Hi everyone, it's John. I'm your TA for the winter quarter. If you're not my student, well, I'm John. I'm one of the TAs. So this series of videos is meant to help or supplement your work in class and also in discussion to help you figure out how to do the problems if you're having any trouble with them. Yeah, that's pretty much the whole point of these. So some of these videos are going to be longer than others. This one should be pretty short, but in general, some will be pretty long, especially near the end with equilibrium stuff. Um, but yeah, so hope it helps. Let's get started. All right, so this is the week 2 worksheet. The week 1 worksheet is the same as the one that I recorded and posted last year. So anyone seeing this, you can find that on my channel, wherever that is. It should be under one of the playlists of the worksheets, CHE2A worksheets. And you should have access to that one. The week 1 discussion was the same. All right, so number 1 here, it says explain the difference between the law of conservation of mass, law or constant composition, and multiple proportions. So first one, and probably in my opinion, the most important one, the law of conservation of mass, at least it's the one that we see the most, or discuss the most. So the law of conservation of mass, I'm not going to write the whole thing, states that mass can neither be created or destroyed. So if you have something and you destroy it or you break it apart, you still have overall the same mass. So this will come into play when we're seeing and balancing chemical reactions and stuff like that, where you should have the same amount of atoms on the left as you do on the right, and so on. Constant composition is just referring to the constant composition of any molecule, meaning that if you find water in your house versus finding water at the creek, still made up of the same things, made up of the same atoms. So same compounds or any compound has the same formula. I'm going to make this very specific. Same molecular formula wherever you find it. I'm kind of out of room here, so I'll do it on the bottom left, and then it says law of multiple proportions. So the law of multiple proportions states that atoms have to be integer ratios of one another, right? So what does that mean? It means that you can't have 0.5 of a hydrogen atom and 1 oxygen molecule. That doesn't work. So you'd have to have at least 1 hydrogen atom and 2 oxygen molecules. But you have to have integer numbers for whatever your molecular compound is. You can't have decimals, you can't have fractions, which are again representations of decimals, but they have to be whole integer numbers. So due to the law of multiple proportions, we're just going to write atoms in a compound will be present in an integer amount per molecule. Great. So for every 1 molecule, you'll have to have some integer of some atom, so on and so forth. I should note positive integer or natural number if you want to be really specific. All right, so number 2, it says fill in the blanks for the elements. Round all atomic masses to the nearest whole number. Element of lithium. So how do you do this? Well, first thing you need is a periodic table. So here's our periodic table. We're going to look for lithium since we are talking about lithium. So how do you determine how many protons lithium has? Well, the way you do that is you just look at the atomic number or the number found at the top above any element on the periodic table. So lithium has an atomic number of 3, as you saw over here. Because of that, it has 3 protons. Great. Number of neutrons, what you do is you round the atomic mass to the nearest whole number. Round up, that's generally the case if you're at 0.5, 0.55. Round up if you're below 0.5, round down, but round to the nearest whole number. So lithium to the nearest whole number has an atomic mass of 7. So the number of neutrons ends up being 4. Well, how did I get that? The mass of any atom, we say, is the number of protons. Put it down here. Number of protons plus the number of neutrons equals the atomic mass. We say electrons are of negligible mass, so we don't count them. They technically do, but we don't count them because they're so small in comparison to protons and neutrons. So number of protons plus the number of neutrons is the atomic mass to the nearest whole number. And then you can just do some algebra here, right? So atomic mass minus the number of protons from each side gives you the number of neutrons, and so on and so forth. Great. So we have 3 protons, 4 neutrons. The number of electrons in a neutral atom is going to be the same as the number of protons. The atomic or molar mass, as we saw a second ago, that is 7. The atomic number is 3. It's going to be the same as the number of protons. Now we're doing carbon. So carbon has an atomic number of 6 over here, and an atomic weight of 12, as you can see. So 6, 6. The atomic mass is 12. The number of neutrons is the number of our atomic mass minus the number of protons, which is 12 minus 6, which is 6. The number of electrons in neutral carbon is 6. In general, assume it's neutral unless you have a charge, which we're going to see in this next one. Great. So for this next one, we have CH3COO minus. So what you want to do is look at each atom individually first, and then treat them all as if they're neutral. And then we'll talk about the charge later. So treat them all like they're neutral, and then find the number of protons and neutrons first. Electrons, wait on, but find the number of protons and neutrons. So carbon, as we saw, has 6 protons and an atomic mass of 12. I'm going to do the protons first just to make things easier. So carbon has 6 protons. Hydrogen has an atomic number of 1. So each one hydrogen has 1 proton. There's 3 hydrogens. So this has 3 protons in total, right? 3 hydrogens. So we have 6 plus 3. I might as well write this out. So number of protons is 6 plus 3 plus 6 for another carbon. Oxygen has 8. It's an atomic number of 8 over here. Plus 8, and there's 2 oxygens, so plus 8 plus 8. You add that up, 12, 15, 23, 31. So there's 31 protons. The atomic mass, we're going to do the same thing that we did before, except just add them all up. So carbon has an atomic mass of 12. If you look at the periodic table. So this is 12 plus 3 plus 12 plus 16 plus 16, which is some number. 24 plus 3 is 27. 27 plus 16 is what, 40, 43. That seems too high. I definitely did my math. No, I didn't. Should actually be 32. So it should be 12 plus 12 plus 3 plus 16 plus 16. And the 2 oxygens. So this has an atomic mass of 59. You take the difference for the number of neutrons and you get 28. Great. Now let's talk about the electrons. So you determine the number of electrons after you do the number of protons. What you do is you look at the overall charge of this molecule. This has an overall charge of -1, right? There's a 1 that's not drawn, but it's an overall charge of -1. So if you remember what the charge of an electron is, the charge of an electron is -1, right? The charge of every proton is +1. In a neutral atom or molecule, the number of protons and the number of electrons are equal. If you have a molecule that has a minus charge, then it means it has more electrons than it has protons. Similarly, if you have a molecule with a positive charge, then it has more protons than it does electrons. So in this case, we have a minus charge, right? It's a -1, which means we have one more electron than we do protons, and that's 32. And that's it. Great. So that's that one. For the next one, sulfur, I think is 16 for the atomic number. It is. So sulfur has 16 protons. Each oxygen has 8, as we just said. So 24 plus 16, that's 40. This is going to end up being 80. This is 40 when you add it all up. Sulfur has a weight of 32. And then you should get that. Yeah, 32 plus 48. That's correct. Then we look at the number of electrons. This is a neutral molecule. I don't see a minus charge here. So it's 40. If it was SO3 minus, then it would be 41. Great. Now it says, which of the following is a halogen? So the halogens on the periodic table are found on the right side here. Really, the ones that you're looking at are fluorine through iodine in this second to last column. And that's your halogen group. So the only one from that group here is fluorine. Rubidium, I think, is a group 1 element. That is correct. So this group 1 we call the alkali metals. Group 2 we call the alkaline earth metals. And there's some metalloids, which I think we'll cover later. But yeah. 4 says describe the significant parts of the periodic table. So we'll break this up into groups, in just the broadest groups. So you have your metals on the left, right? Then you have your transition metals kind of in this middle block here. Those are always going to be the weird ones when you have problems or homework or whatever else. Then you have kind of these metalloids, which sit on top of the staircase. So these are your metalloids. This other block, those are your nonmetals. And then on this last column, these are your noble gases. And then that's it. There's different ways you could split it up. There's a lot of things that are, excuse me, significant about the periodic table. I'm just going to split it up on the broadest groups because I think that's what's being asked. So metals, and there's actinides on the bottom, but we won't talk about that. So metals, transition metals, metalloids, nonmetals, noble gases. Great, no, that's it. 5 says, which of the following transition metal cations have both a +2 and a +3 as common charges? So I don't believe this is something you will be given on a test. That is correct. So this is going to be something that you will just have to memorize. So the one with +2 and +3 is going to be common copper and chromium. Those both have those as common charges. That just ends up becoming a memorizing thing. I'm sure you have probably seen a list by now. Dr. Chamberlain has probably given it on things to memorize. It's probably on there. This is going to be one of them. So there are some transition metals that you are just going to want to remember the common charges there. Number 6, it says, what is the molecular formula of morphine? So how do you figure out what the molecular formula is? What you're doing is you're counting the number of atoms in every type of atom and then writing it out. That's what it is. So how do you read this? This drawing is a line and stick drawing. We typically use these in organic chemistry to represent molecules because Lewis structures would be way too hefty, and these are just very nice. So how do you do this? Every vertex that you see is a carbon atom, right? We don't write in C, again, just because it's easier not to write in a bunch of carbons. But every vertex is a carbon, okay? So let's start with that. Well, I have 1, 2, 3, 4, 5, 6. I should also note, I forgot to note, these lines between each vertex indicate bonds. Yeah, so like this is a bond between these two carbons. This is a double bond between these other two carbons. So two lines indicate a double bond, and so on and so forth. So back to counting carbons: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This little bold line, there's a vertex here. 15, 16. Did I lose track? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I did lose track. So it looks like there's 17 carbons. So how do we indicate that? The first part of our formula is going to be C subscript 17. The subscript indicates how many carbons or how many of some atom type we have in our molecule. So next, we get to count. Yeah, you can do any of them. I'm just going to do nitrogen because it's easy. There's one. So we got one nitrogen. Also to note, these little bold lines, what do they mean? It just means it's a type of geometric and it's how we display geometry on a flat page. So bold lines indicate that it's coming out of the page towards you. So if you can imagine this is flat, but then wherever there's a bold line, it starts to stick out at you. And then dashed lines indicate the opposite, where it's going into the page or away from you. You don't really have to worry about that. You can just treat it as normal lines. Unless you take organic chemistry, then it'll be important for stereochemistry. So there's one nitrogen, there's 1, 2, 3 oxygens, so NO3, and then we get to count all the hydrogens. Well, it may be tempting to just say, okay, well, that's easy. 1, 2, 3, 4, 5, 6, 7, done. Not done. So how do you count the number of hydrogens? There are some that are not drawn in here. Again, the reason we use this method of drawing in organic chemistry is because there's so many carbons and there's so many hydrogens. So we abide by certain rules to make it easier to look at things. So every carbon in this structure has 4 bonds, whether or not they're drawn. In general, you can assume carbon has 4 bonds. You're not going to have to worry about carbocations or anions until organic chemistry. So assume carbon has 4 bonds if you see a picture like this. Since you assume every carbon has 4 bonds, there are obviously bonds missing. If you look at this carbon, this one has 3 bonds. It has a double bond to this carbon and a single bond here, right? This carbon only has 2 bonds. So where's the others? Every bond that's not drawn in with a carbon is a bond to hydrogen. It's just one of the rules that we use. So if you have a carbon, you do not have to draw the hydrogens in. If you label it with a C, then you do. Don't have to worry about that. But if you have a carbon, you don't have to draw on the hydrogens. If it's not carbon, you do, which is why you see it in all these other spots. Well, this one's actually a carbon, just makes it easier to see the geometry. But for that O, you need to write it in. This one, they actually did not have to write it in. But for carbons, you don't have to draw on the hydrogens. So if we were to draw in some of these hydrogens, like that's one, that's another one. This carbon already has 4 bonds, so there's not a hydrogen there. This one also already has 4 bonds. This one has 1, 2, already has 4 bonds. This one also already has 4 bonds. So there's 2 hydrogens up here. And then this carbon here has 2 other hydrogens because it only has 2 bonds currently. So we have 4 total. And then this one has another hydrogen over here. So 5. There's 8 now because we have 3 from that carbon. Has 4 bonds total. 1 to each hydrogen if you were to draw it out. Be like this. And then 1 to the nitrogen. This carbon has 2 more. This one has 2 more as well. So let's tally this up before I lose track. One with that one. So we have 1, 2, 3, 4, 5, 8, 10, 12, 13. So there's 13 hydrogens so far. I haven't done the bottom ring yet. So over here, we're at 13. So that's another hydrogen, right? That's another one. It's missing. That's also another one. And again, I'm just trying to get every carbon to have 4 bonds is really what it is. So 13 plus 3 should be 16. So I just went ahead and recounted it. I missed one. So we have 17 hydrogens overall from carbons. Then you do have these ones that I didn't count yet, which are connected to oxygens. And so in total, we have 19 hydrogens. And then this problem is done. Going on to the next page, it says indicate the oxidation state of the underlined element. Remember, there are exceptions. All right, so how do you do this? In general, you want to go off of elements you know the oxidation state of are ones that don't change. So in general, group 1 elements are going to be +1. Now, I should note group 1 elements that are not hydrogen. So everything here will always be a +1. So you will never see lithium as a +2 or a minus anything. Lithium is always a +1. Sodium is always a +1. Potassium is always a +1. Rubidium is always a +1. Cesium is always a +1, right? And so on and so forth. So generally, you want to go off of the things that you know. Again, group 2 is actually going to be very similar. These are always going to be a +2, right? Similarly with the halogens, these are always going to be a +1. The ones that get, or -1, my bad. Those are always going to be a -1. Oxygen usually is a 2-. It's not always. Nitrogen's usually a 3-, and then carbon is kind of the iffy one. So go off of the things that you do know. And there's also some polyatomic ions, which we do not have, that you are going to want to know. So like ammonium, so NH4 plus, that always has a +1. OH- always has a -1. So you want to look at everything else before determining the oxidation state of whatever you're looking at. So if we go back here, we're going to assume that the carbon is the one I don't know. And we're going to assume hydrogen is a +1. It usually is. Usually. So looking at this, let's assume the hydrogen is a +1. There are 4 of them. So hydrogen contributes +4 to this molecule, right, in terms of charge. Then the carbon has to balance that out. So it's going to be 4- or -4. Don't really know why the convention is often the sign after the number. It doesn't really matter. So they're just indicating that or -4, -4 charge, whatever. So carbon has an oxidation state of 4- or -4. Although to make this more clear, also for myself, whenever we do math, I'm going to actually put the negative before. So if Dr. Chamberlain uses different notation or somebody else does, no, it just means basically the same thing. I just like putting it before. All right, next we're going to look at sulfur in terms of sulfur fluoride or sulfur tetrafluoride. So fluorine always has a -1 if you look at the periodic table. So always in the second to last group, always a -1, no matter what. So fluorine's always a -1. This whole thing has a charge of 0. What does the charge or oxidation state of sulfur have to be? Has to be 4, +4, right? To cancel out. Again, there's 4 fluorines, each is -1. -1 times 4 is -4. And then -4, if you want to do in terms of math, -4 plus x is equal to 0, x is equal to 4. And then you have sodium oxide, Na2O2. Okay, so sodium, as I said, is always a +1, no matter what, period paragraph, right? It's always in this group 1, below lithium. It's always a +1. So if you have 2 +1 sodiums, and then there's 2 of them, you get +2 from sodiums. That means that the oxygens have to balance out with a +2. There's 2 oxygens. So each oxygen has to be a -1. Again, if you prefer to think of it in terms of an equation, you can say, well, +2 or +2, right? Doesn't really matter what convention you use, plus 2x, whatever the charge of oxygen is x, is equal to 0. Then you can just solve for x. X becomes -1. All right, D, it says you have potassium permanganate. So KMNO4. Potassium, we always know, is a +1. No matter what, it's in group 1. So I think below sodium. Oxygen is usually a 2-. Now, if you don't assume oxygen is a 2- here, there's no way for you to do this problem. So let's assume oxygen is a 2-, again, because we need to figure out what manganese is. And if you have to figure out what manganese is, I know what potassium is. I have to make some sort of guess as to what oxygen is. Again, why 2-? It's in the second to last, or I guess third to last, technically, column on the periodic table. So 2 columns away from the noble gases. So let's assume oxygen is a 2- or -2. There are 4 of them, so they contribute -8 in total. Overall, this thing has a charge of 0. If you add up potassium and oxygen, then you figure out, well, the total charge contribution is -7, -8 plus 1, right? So from oxygens and potassium, you get -7. And the manganese has to balance that out, go to 0, so you get +7. And that's it. On to E. Doing the same thing, water is neutral. Water has a charge of 0. NH4 has a charge of +1. There are 2 of them. So this gets an overall charge of +2. Oops. +2 from the NH4 in the water. So overall, though, this is a +4 or a 4+. Again, I'm putting them before. I just like putting it before better. So overall, it's a 4+, right, or a +4. That means platinum has to be a +2. 2 + 2 gives you 4, +4. So that's how we get that. Then we have molybdenum, what is it? Molybdenum hydroxide ammonia. So something like that. NH3 is neutral. This is 0. NH4 is +1. So taking away one of the hydrogens goes down a charge. OH is a -1. There are 4 of them. I think you can kind of see where this is going. Overall, the charge contribution to this molecule, that's everything except molybdenum, is -4. Then overall, this has a charge of 2+. So molybdenum has to be what charge? Actually, let's make it a little more general. 3 molybdenums from this molecule have to have overall what charge? The answer is 6, right? So these 3 must contribute a +6. -4 plus 6 gives you +2. If it helps write the equation out, you can write -4 plus x, or 3x if you want the charge of each molybdenum, which we're going to do right now, is equal to 2, and you can solve like that. Do whatever is easiest. So this is +6, and then there's 3 of them. So you divide by 3, and you get 2. So each one has a +2 charge. That's it. Going on to the next one, it says name the following compounds. So how do you do this? If you have an H in the beginning, oftentimes it indicates some sort of acid. Now, not always, but generally speaking. So if you have an H bonded to like some non-metal in general, it's usually going to be an acid. Usually. So if we look at this one, it says HClO2. So this is probably on the list of things to memorize. the different series of different types of molecules. So there is the ClO series or whatever. ClO is hypochlorite when you're naming without the hydrogen. So ClO is hypochlorite, ClO2 is chlorite, ClO3 is chlorate, and then ClO4 is perchlorate. So you just you have to remember the ends no matter what. So lower in the series ends with an ite, higher ends with an ate. If it's the highest in the series, you add a per in the beginning. It's the lowest. I think the chlorate series is chlorite, whatever, is the longest series. Probably wrong on that, but I think that's the longest one that you learn with 4 of them. So higher ones end with 8, lower ones end with ite. If it's the way I think about it is there's 2 in the middle. So ClO2 and ClO3 are in the middle in terms of a number of oxygens, right? Versus ClO and ClO4. ClO, so the lowest one, you put hypo in the beginning, so hypochlorite. And then ClO4, ClO3 ends with chlorate, right? Or 8. You add a per in the beginning, so perchlorate. So if you remember the first 2 or the middle 2, then you'll know the suffix at the end. If you don't know the middle 2, then I guess you can just memorize all of them. But that's an kind of easier way to memorize it. Anyways, let's go back to the problem here. So we have HClO2. If you have something that's that ends with ite, then when you're writing it as an acid here, so this is an acid, HClO2, what you're going to write instead of ite is you're going to write us. So this is going to be chlorus, and then acid, because there's that H in the beginning, bond with this. This is chlorus acid. If it was ClO, it would be hypochlorous acid. If it's ClO3, it would be chloric acid. So instead of 8, you replace it with an ic. And then so on and so forth. Next, we have hydrogen selenide. So hydrogen is over here in group 1, as you probably already spoiled the name. Hydrogen is in group 1. Then you have selenium in the non-metal section over here. So how do you name it? Well, hydrogen is not a metal. It's a non-metal. But the way you can name this, so if you have 2 non-metals, sorry, not 2 non-metals. If you have a metal and a non-metal, or hydrogen with a non-metal that doesn't form, something acidic, then how you name it is you put the name of the metal, or in this case, hydrogen, and then you put the name of the non-metal, except end it with "ide." So hydrogen selenide. HCl is hydrogen chloride. HO is, hydrogen oxide. I think you'll get into naming of non-metals later. So HNO2, the way you name that. So if you look at the series, I don't have it with me, so it's something you're gonna have to memorize. There's NO2 and NO3. So NO2 is nitrite. NO3 is nitrate. So again, similar thing with the ClO series. ClO2 is chlorite. ClO3 is chlorate. So this is nitrite. So how do we name this one? This is an acid. It's HNO3. This is going to be nitrous. So removing the ite, replacing with an us acid. And that's it. Then D, so this one, let's see, we have a metal and a non-metal. So you have strontium and oxygen. So this is strontium oxide. So this is the one where you have a metal and non-metal. You just say the name of the metal, then part of the non-metal, then I'd end it with I'd. E, it says K2CrO4. If you're wondering where you put the I'd, I guess it just comes with experience. Like, I guess whatever sounds right, OY doesn't really sound right. You generally keep most of the letters from the element before putting the I. Same with like fluoride, right? Um, Fluoride and so on. So E, it says we have that K2CrO4. So how do we name it? So probably under the list of things to memorize is the CrO4 polyatomic ion. The CrO4 polyatomic ion is chromate. So how do we name it? Well, potassium is the metal. And this is true for polyatomic ions too. You're just going to put the name of the metal and then the name of the polyatomic ion. So potassium hydroxide is another one. So on and so forth. So this is potassium chromate. Done. Then we have CR2O3. So that one, because chromium is a transition metal, you do want to be careful. When you have a transition metal, you need to make sure that you're labeling what is the oxidation state of the transition metal. So how do you figure that out? Well, you can look above, go back. Oh, I missed one. I missed G. Sorry. So we'll finish F and then we'll go back to G. So you can look above for how to do that, and then we'll go back to G. So we have CR2O3. So first you find the oxidation state of the transition metal. We're going to assume oxygen is 2- here. The chromium ends up being a +3 each to balance out the charges. So the way you name it is you put the name of the metal, chromium. You put the oxidation state, 3 in Roman numerals. And then you end up with the oxide again. So chromium 3 oxide. Then that's it. Going back to G here. So this is one of the exceptions where hydrogen is not +1. Magnesium is always a +2 though, which means each hydrogen has to be a -1, right, to balance this out. Magnesium, again, it's one of those elements. It's in the first two groups. That's not hydrogen, which will always be a +1 or a +2. So the hydrogen has to be a -1 for this to balance out and be neutral. Great, going back to G. Same thing, same idea here. So first you have to figure out what the transition metal charge is. So Fe is iron. Iron, and then SO4 should have a charge of, should be 2-. Let me double check. That is correct. So SO4 is a 2-. So this is what? 2- times 3 is -6. There's 2 iron, so each iron, again, has to be a +3. So iron 3, and then this is sulfate. Done. Next, we're naming this one. So you have NH4, 2 of them, and then HPO4. So the first part is a polyatomic ion. That's actually a positive one. So we're actually just going to put the name of this one. You can also kind of see this trend here, right? Generally, the things with the positive charge go first. Generally true, not always, but generally the things with the positive charge go first, and then whatever follows has the negative charge, whatever it's attached to. So this is ammonium. And then HPO4. So PO4 is phosphate. There's a hydrogen attached to it. So how do we name it? Kind of how you were naming it before. So this is hydrogen phosphate for that last part. So this is ammonium, hydrogen phosphate. Then that's it. All right, number 9, it says write the formulas for the following compounds: lead 2 perchlorate, hydriodic acid, chlorous acid, so on and so forth. So starting with the first one, lead has a symbol of Pb. And then there is perchlorate. So again, going back to what we were talking about before, perchlorate is ClO4. Great. Now, what is the charge of perchlorate? The charge of perchlorate should be -1. So how do you balance these out? Well, the perchlorate has a charge of -1. The lead has a charge of 2. So to balance that out, I need 2 perchlorates. So it's kind of like doing the oxidation thing that we just did above, except backwards. B, it says we have hydroiodic acid. High. And then that's done. So hydro indicates the hydrogen. The iodic acid indicates, again, hydrogen's in there, bonded with iodine. That's the iodic part. Both have a charge of 1. And then this is done. Chlorous acid we actually did above. So that's HClO2. You know it's ClO2 because it ends with an us, right? You go from you can think of it in terms of ite to us or us to ite, but ite is an O2 compound, same with us. So chlorous acid has O2, and then there's a hydrogen because it's an acid. Then there's sodium hydrogen sulfite. Start with a metal, sodium, and then hydrogen sulfite. So hydrogen sulfite is HSO3, since SO4 is sulfate, SO3 is sulfite. And then overall, the charge, I believe, is -1. This is going to be something you want to remember in case it comes up on your test. That is correct. It is a -1. So that's it. The charge is balanced out already. Sodium is a +1. Hydrogen sulfide's -1. And also I should note, right, these have coefficients of 1 that I'm just not writing in. So +1 and -1 cancel. Then we have dinitrogen tetraoxide. So this is naming 2 nonmetals together. If you have 2 nonmetals, you put whatever the first one is. So nitrogen, and then you have a prefix. The prefix indicates how much there is. So dinitrogen indicates 2. Tetraoxide indicates 4 oxygens. That's it. N2O4. Then we have disulfur dichloride. Same thing, same naming. 2 nonmetals. There's 2 sulfurs, disulfur, dichloride, 2 chlorides. Last one, it says which of the following compounds would most likely contain a metal as one of the elements? So going off of based off what you probably know, the one that contains a metal always is ionic, right? Ionic compounds always have a metal and a non-metal. So this is the best answer here. All right, well, that is it for this video. I hope that helps. And maybe see you in the next one.